Now, in general, an exponential function will look like 2 to the x and 3 to the x. It'll go through this point 0, 1. It'll go up on the other side, down on the other side. We're going to assume, for convenience, that this b is larger than 1 for convenience. But we notice that this will satisfy the horizontal line test. Now, what does that mean if it satisfies the horizontal line test? That means f inverse exists. So let's write that down. In general, f of x equals b to the x with b greater than 1 satisfies the horizontal line test. And because of that, f inverse of x exists. So its inverse exists. Let's define it. We denote f inverse of x for exponential function b to the x by this notation. Log of x with base b. Log of x with a subscript b underneath logarithm, or underneath log. Log is short for the word logarithm. So the logarithmic functions are defined only for b greater than 1. These are bases of the logarithm, just as this is a base of the exponential function. The logarithm takes as its base only numbers larger than 1. Now, what does the graph of this logarithm look like? Well, we flip the exponential function across the line y equals x. So in particular, this point 0, 1 is going to go over to 1, 0, and it'll look like this. So right here is the logarithm. I should have used the notation y equals b to the x up there. That kind of simplifies things, because you don't have to write a bunch of f's and g's and f inverses. So I'm going to call this just the set of points that satisfy y equal b to the x. And then this right here is the set of points that satisfy y equals log of x with base b. If I can't fit that in. Y equals log of x with base b. There. So the logarithm is the inverse of an exponential function. Now, we're going to be doing calculus with logarithms, but we will also need some computations with logarithms. And to do those computations, let's look at the logarithm properties. Properties of logarithms. Let's look at 2 of them. Well, let's look at 3 of them. The third one's a consequence of the first 2. Log with base b of x times y. The logarithm of something times another splits into the sum of 2 logarithms. Logarithm of a product splits into the sum of logarithms. The next one, logarithm with base b of x to some number. This exponent comes in front as a product. So you get r times log of x with base b. So logarithm of x to the r comes out in front as a product. Now you can combine these 2 properties to give you a third property. And maybe I won't even call it 3. I might just call it additional logarithm property, because it is a consequence of this for r being negative. So additional additionally, we have this observation, which you could view as a property. Logarithm with base b of a quotient is logarithm of the difference. So, this is combining the first two properties with a negative exponent on this y, a negative 1 on that y as an exponent. And we'll see how we use these in a couple problems. Which couple problems? Well, let's find them. I think they're right here. We'll do this. We'll solve some equations for x. So example, solve this equation for x. Log of root x with base 10 plus log of x with base 10 equals 2. So solve this for x, and in this computation we're going to keep in the back of our mind that logarithms are inverse functions for exponentials. And we'll see where that comes into play in a moment. Now, right here, there are two different ways you could start. I will do one of them. Some of you might do the other one. The first thing I will notice is that we can rewrite this root x as x to the 1/2. Now, if you can write this as x to the 1/2, we can use Logarithm Property 2, which says you can bring that x, or you can bring that 1/2 out front using multiplication. So this is x to the 1/2. Use Property 2 to bring that half out front. And we'll leave that next piece alone, equals 2. Well, what can we do with this? You could have, in step 1, used Property 1 also, I should mention. But I used Property 2. Now, what do we have here? We have half of something. And we have 1 of something. If you have half of something and 1 of something, then you have 1.5 of those. 1.5 is also known as 3/2. So we have 1.5 of these log. We have half of a log x. We have a full log x. So you have 1.5 log x's, which is 3/2 log x. Now this equals 2. We can get rid of this 3/2 by multiplying everything by 2/3. So 2/3 multiplied by 2 divided by 3. Multiply the entire equation by 2/3. The right side you get 4/3. The left side you get just log of x with base 10. Now how would we solve this for x? Well, I have to erase the top of this board because I'm at the bottom of the board now. How would we solve this for x? Let's just write it in the middle of one board. Log x with base 10 equals 4/3. We want to solve that for x. In other words, we want to get rid of this logarithm. How do we get rid of a logarithm? Well, we defined logarithms to be the inverse of exponential functions. So a logarithm and an exponential cancel each other out, just like, maybe not just like, quite similar to how we can get rid of this 2 by multiplying by 1/2. We can get rid of that logarithm by taking an exponential. Which exponential? Well, it tells us, 10. So take 10 to this left side, take 10 to this right side, 10 to the left side, you're just left with x. 10 to the left side, just x. 10 to the right side is 10 to the 4/3. which is a perfectly fine number. Now, with these logarithms, you could use any base larger than 1, and those logarithm properties will still hold. But in math, in calculus especially, there's a certain logarithm which is much more convenient than others. We will see in Chapter 3 and in Chapter 4 why this certain logarithm is more convenient than others. But for now, I'll just leave it as a remark. Remark. There is an important number called E, which is approximately 2.71, what numbers did I write here? 2.718 is all I wrote in my notes. I don't know after that. There's an important number called E. And log with this base E, notice that's larger than 1. Log with base E is abbreviated ln. Log of x with base E is rewritten ln of x, and it's read the natural logarithm, and is called the natural logarithm of x, in that case, since it's of x. And let's just look at an example. Solve this for x. Solve this for x. Solve for x. What are we solving for x? ln 1 over x equals 4. Natural log 1 over x equals 4. Well, there are, again, a couple first steps you could use depending on which logarithm properties you're more comfortable using. I'm going to first get rid of the natural log. So remember, exponential functions get rid of natural logs, or get rid of logs. So exponential functions with base E will get rid of natural logs. In other words, raise both sides of this equation, raise E to both sides of this equation. E to the left side is 1 over x. E to the right side is e to the 4th. And now we want to solve this for x. Well, how would you solve it for x? I would multiply both sides by x, divide by e. In other words, just flip both sides around. And you get x equals 1 over e to the 4th. Which, if you wanted, you could write that as e to the negative 4th. I'll just leave it as 1 over e to the 4th because this shows both sides flipping around. So in Chapter 1, we're going to use all of these functions throughout the semester as we do calculus. So it's good to be familiar with trig functions, logarithms, exponential functions, especially natural logarithms. We'll use this. We will use logarithms with other bases, but we will use more logarithms with this base.